An atomic orbital is a mathematical function that describes the wave-like behavior of either one electron or a pair of electrons in an atom. This function can be used to calculate the probability of finding any electron of an atom in any specific region around the atom's nucleus. The term may also refer to the physical region or space where the electron can be calculated to be present, as defined by the particular mathematical form of the orbital. Each orbital in an atom is characterized by a unique set of values of the three quantum numbers n and m, which respectively correspond to the electron's energy, angular momentum, and an angular momentum vector component. Any orbital can be occupied by a maximum of 2 electrons, each with its own spin quantum number s. These names, together with the value of n, are used to describe the electron configurations of atoms. They are derived from the description by early spectroscopists of certain series of alkali metal spectroscopic lines as sharp, principal, diffuse, and fundamental. Orbitals for greater than 3 continue alphabetically, omitting J. Atomic orbitals are the basic building blocks of the atomic orbital model, a modern framework for visualizing the submicroscopic behavior of electrons in matter. In this model, the electron cloud of a multi-electron atom may be seen as being built up in an electron configuration that is a product of simpler, hydrogen-like atomic orbitals. The repeating periodicity of the blocks of 2, 6, 10, and 14 elements within sections of the periodic table arises naturally from the total number of electrons that occupy a complete set of s, p, d and f atomic orbitals, respectively, although for higher values of the quantum number n, particularly when the atom in question bears a positive charge, the energies of certain subshells became very similar, and so the order in which they are said to be populated by electrons can only be rationalized, somewhat arbitrarily. Electron properties. With the development of quantum mechanics and experimental findings, it was found that the orbiting electrons around a nucleus could not be fully described as particles, but needed to be explained by the wave-particle duality. In this sense, the electrons have the following properties. Wave-like properties. The electrons do not orbit the nucleus in the sense of a planet orbiting the Sun, but instead exist as standing waves. The lowest possible energy an electron can take is therefore analogous to the fundamental frequency of a wave on a string. Higher energy states are then similar to harmonics of the fundamental frequency. The electrons are never in a single point location, although the probability of interacting with the electron at a single point can be found from the wave function of the electron. Particle-like properties. There is always an integer number of electrons orbiting the nucleus. Electrons jump between orbitals in a particle-like fashion. For example, if a single photon strikes the electrons, only a single electron changes states in response to the photon. The electrons retain particle-like properties such as each wave state has the same electrical charge as the electron particle. Each wave state has a single discrete spin. Thus, despite the obvious analogy to planets revolving around the Sun, electrons cannot be described simply as solid particles. In addition, atomic orbitals do not closely resemble a planet's elliptical path in ordinary atoms. A more accurate analogy might be that of a large and often oddly shaped atmosphere, distributed around a relatively tiny planet. Atomic orbitals exactly describe the shape of this atmosphere only when a single electron is present in an atom. When more electrons are added to a single atom, the additional electrons tend to more evenly fill in a volume of space around the nucleus, so that the resulting collection tends toward a generally spherical zone of probability describing where the atom's electrons will be found. Formal quantum mechanical definition. Atomic orbitals may be defined more precisely in formal quantum mechanical language. Specifically, in quantum mechanics, the state of an atom, i.e., an eigenstate of the atomic Hamiltonian, is approximated by an expansion into linear combinations of antisymmetrized products of one-electron functions. The spatial components of these one-electron functions are called atomic orbitals. A state is actually a function of the coordinates of all the electrons, so that their motion is correlated. But this is often approximated by this independent particle model of products of single electron wave functions. In atomic physics, the atomic spectral lines correspond to transitions between quantum states of an atom. These states are labeled by a set of quantum numbers summarized in the term symbol and usually associated with particular electron configurations, i.e., by occupation schemes of atomic orbitals. This notation means that the corresponding Slater determinants have a clear higher weight in the configuration interaction expansion. The atomic orbital concept is therefore a key concept for visualizing the excitation process associated with a given transition. For example, one can say for a given transition that it corresponds to the excitation of an electron from an occupied orbital to a given unoccupied orbital. Nevertheless, one has to keep in mind that electrons are fermions ruled by the Pauli exclusion principle and cannot be distinguished from the other electrons in the atom. Moreover, it sometimes happens that the configuration interaction expansion converges very slowly and that one cannot speak about simple one-determinant wave function at all. This is the case when electron correlation is large. Fundamentally, an atomic orbital is a one-electron wave function, even though most electrons do not exist in one-electron atoms. And so the one-electron view is an approximation. When thinking about orbitals, we are often given an orbital vision which is heavily influenced by this Hartree-Fock approximation, which is one way to reduce the complexities of molecular orbital theory. Types of orbitals. Atomic orbitals can be the hydrogen-like orbitals, which are exact solutions to the Schrödinger equation for a hydrogen-like atom. Alternatively, atomic orbitals refer to functions that depend on the coordinates of one electron but are used as starting points for approximating wave functions that depend on the simultaneous coordinates of all the electrons in an atom or molecule. The coordinate systems chosen for atomic orbitals are usually spherical coordinates in atoms and Cartesians in polyatomic molecules. The advantage of spherical coordinates is that an orbital wave function is a product of three factors each dependent on a single coordinate. Psi equals r theta phi. The angular factors of atomic orbitals theta phi generate s, p, d, etc. functions as real combinations of spherical harmonics ym. There are typically three mathematical forms for the radial functions r which can be chosen as a starting point for the calculation of the properties of atoms and molecules with many electrons. The hydrogen-like atomic orbitals are derived from the exact solution of the Schrödinger equation for one electron and a nucleus. For a hydrogen-like atom, the part of the function that depends on the distance from the nucleus has nodes and decays as E-. The Slater-type orbital is a form without radial nodes but decays from the nucleus as does the hydrogen-like orbital. The form of the Gaussian-type orbital has no radial nodes and decays as E. Although hydrogen-like orbitals are still used as pedagogical tools, the advent of computers has made STOs preferable for atoms and diatomic molecules since combinations of STOs can replace the nodes in hydrogen-like atomic orbital. Gaussians are typically used in molecules with three or more atoms. Although not as accurate by themselves as STOs, combinations of many Gaussians can attain the accuracy of hydrogen-like orbitals. History. The term orbital was coined by Robert Mulliken in 1932 as an abbreviation for one electron orbital wave function. However, the idea that electrons might revolve around a compact nucleus with definite angular momentum was convincingly argued at least 19 years earlier by Niels Bohr, and the Japanese physicist Hantaro Nagaoka published an orbit-based hypothesis for electronic behavior as early as 1904. Explaining the behavior of these electron orbits was one of the driving forces behind the development of quantum mechanics. early models with J.J. Thomson's discovery of the electron in 1897, it became clear that atoms were not the smallest building blocks of nature, but were rather composite particles. The newly discovered structure within atoms tempted many to imagine how the atom's constituent parts might interact with each other. Thomson theorized that multiple electrons revolved in orbit-like rings within a positively charged jelly-like substance. And between the electron's discovery in 1909, this plum pudding model was the most widely accepted explanation of atomic structure. Shortly after Thomson's discovery, Hantaro Nagaoka, a Japanese physicist, predicted a different model for electronic structure. Unlike the plum pudding model, the positive charge in Nagaoka's Saturnian model was concentrated into a central core, pulling the electrons into circular orbits reminiscent of Saturn's rings. Few people took notice of Nagaoka's work at the time, and Nagaoka himself recognized a fundamental defect in the theory even at its conception, namely that a classical charged object cannot sustain orbital motion because it is accelerating and therefore loses energy due to electromagnetic radiation. Nevertheless, the Saturnian model turned out to have more in common with modern theory than any of its contemporaries. Bohr atom in 1909, Ernest Rutherford discovered that the bulk of the atomic mass was tightly condensed into a nucleus, which was also found to be positively charged. It became clear from his analysis in 1911 that the plum pudding model could not explain atomic structure. In 1913, as Rutherford's postdoctoral student, Niels Bohr proposed a new model of the atom, wherein electrons orbited the nucleus with classical periods, but were only permitted to have discrete values of angular momentum, quantized in units h, 2 pi. This constraint automatically permitted only certain values of electron energies. The Bohr model of the atom fixed the problem of energy loss from radiation from a ground state, and more importantly explained the origin of spectral lines. After Bohr's use of Einstein's explanation of the photoelectric effect to relate energy levels in atoms with the wavelength of emitted light, the connection between the structure of electrons in atoms and the emission and absorption spectra of atoms became an increasingly useful tool in the understanding of electrons in atoms. The most prominent feature of emission and absorption spectra was that these atomic spectra contained discrete lines. The significance of the Bohr model was that it related the lines in emission and absorption spectra to the energy differences between the orbits that electrons could take around an atom. This was, however, not achieved by Bohr through giving the electrons some kind of wave-like properties, since the idea that electrons could behave as matter waves was not suggested until 11 years later. Still, the Bohr model's use of quantized angular momenta, and therefore quantized energy levels, was a significant step towards the understanding of electrons in atoms, and also a significant step towards the development of quantum mechanics in suggesting that quantized restraints must account for all discontinuous energy levels and spectra in atoms. With de Broglie's suggestion of the existence of electron matter waves in 1924, and for a short time before the full 1926 Schrödinger equation treatment of hydrogen-like atom, a Bohr electron wavelength could be seen to be a function of its momentum, and thus a Bohr orbiting electron was seen to orbit in a circle at a multiple of its half-wavelength. The Bohr model for a short time could be seen as a classical model with an additional constraint provided by the wavelength argument. However, this period was immediately superseded by the full three-dimensional wave mechanics of 1926. In our current understanding of physics, the Bohr model is called a semi-classical model because of its quantization of angular momentum, not primarily because of its relationship with electron wavelength, which appeared in hindsight a dozen years after the Bohr model was proposed. The Bohr model was able to explain the emission and absorption spectra of hydrogen, the energies of electrons in the n equals 1, 2, 3, etc. states in the Bohr model match those of current physics. However, this did not explain similarities between different atoms, as expressed by the periodic table, such as the fact that helium, neon, and argon exhibit similar chemical inertness. Modern quantum mechanics explains this in terms of electron shells and subshells, which can each hold a number of electrons determined by the Pauli exclusion principle. Thus the n equals 1 state can hold 1 or 2 electrons, while the n equals 2 state can hold up to 8 electrons in 2s and 2p subshells. In helium, all n equals 1 states are fully occupied, the same for n equals 1 and n equals 2 in neon. In argon, the 3s and 3p subshells are similarly fully occupied by 8 electrons. Quantum mechanics also allows a 3d subshell, but this is at higher energy than the 3s and 3p in argon and remains empty. Modern conceptions and connections to the Heisenberg uncertainty principle. Immediately after Heisenberg discovered his uncertainty relation, it was noted by Bohr that the existence of any sort of wave packet implies uncertainty in the wave frequency and wavelength, since a spread of frequencies is needed to create the packet itself. In quantum mechanics, where all particle momenta are associated with waves, it is the formation of such a wave packet which localizes the wave, and thus the particle, in space. In states where a quantum mechanical particle is bound, it must be localized as a wave packet, and the existence of the packet and its minimum size implies a spread and minimal value in particle wavelength, and thus also momentum and energy. In quantum mechanics, as a particle is localized to a smaller region in space, the associated compressed wave packet requires a larger and larger range of momenta, and thus larger kinetic energy. Thus, the binding energy to contain or trap a particle in a smaller region of space increases without bound. As the region of space grows smaller, particles cannot be restricted to a geometric point in space, since this would require an infinite particle momentum. In chemistry, Schrödinger, Pauling, Mulliken and others noted that the consequence of Heisenberg's relation was that the electron, as a wave packet, could not be considered to have an exact location in its orbital. Max Born suggested that the electron's position needed to be described by a probability distribution which was connected with finding the electron at some point in the wave function which described its associated wave packet. The new quantum mechanics did not give exact results, but only the probabilities for the occurrence of a variety of possible such results. Heisenberg held that the path of a moving particle has no meaning if we cannot observe it, as we cannot with electrons in an atom. In the quantum picture of Heisenberg, Schrödinger, and others, the Bohr atom number and for each orbital became known as an n-sphere in a three-dimensional atom and was pictured as the mean energy of the probability cloud of the electron's wave packet which surrounded the atom. Orbital names. Orbitals are given names in the form, where x is the energy level corresponding to the principal quantum number n. Type is a lowercase letter denoting the shape or subshell of the orbital and it corresponds to the angular quantum number, and y is the number of electrons in that orbital. For example, the orbital 1s2 has 2 electrons and is the lowest energy level and has an angular quantum number of equals 0. In X-ray notation, the principal quantum number is given a letter associated with it. For n equals 1, 2, 3, 4, 5, the letters associated with those numbers are K, L, M, N, O, respectively.